Okay, thank you. I changed the title because I think this title goes better with the day, because all my talk will be around the conjecture of Mazur, and also a collaborator of mine is a recent student of Alexander Goncharov, Vasilin Dimitrov. Okay, so first of all, the motivation is let's start with Faltings' theorem. In my whole talk, I'll fix G to be a number to be an integer at least 2, and C is a smooth, projective, irreducible curve defined over Q bar. The motivation is first, Faltings proved in 1983 that if C has genus at least 2 defined over a number field K of degree D, then C has finitely many rational points. So this is the Mordell conjecture. This proof also gives a sort of ad hoc upper bound on this number. It's on G and D and the Faltings height and the Abel-Jacobi rank and so on, but the bound is really not explicit and an ad hoc one. Around 90s, Vojta gave a new proof to Faltings' theorem using Arklov geometry, and more in the sense of Dufresne-Time method, which was simplified by Faltings and further simplified by Bombieri, purely in terms of Dufresne-Time geometry. It's a new proof of the same result, but also at the same time gives a rather good bound on it. So the bound is, in terms of the genus, the degree of the number field, the Faltings height of the Jacobian of this curve, and the Mordell weight rank. All these numbers are explicit in this bound, and later on the bound was improved by David Philippon and Raymond and so on, but it remains in this term.
So this is in theory, this kind of a computable expression.
Yes.
It doesn't involve, but on the other hand, the height of the points is not known to be.
No. This is not. That is effective version, but no. Yeah. Mazur asked the following question. First of all, in 96, this is a conjecture. Later on, it was simplified. I will state it in its most general form, maybe here, because this is the conjecture I'm going to study. Let's take any algebraic point P0 in C, and let's consider the Abel-Jacobi embedding via this point. We take any finite rank subgroup of JQ bar, say of rank R. Then we hope that the cardinality of the following points, the points on C, intersect this finite rank subgroup. It has a sort of not really uniform, but it's not uniform only in terms of the rank. So this bound does not depend on the choice of the point, first of all, and also it does not depend on the finite rank subgroup as long as the rank is fixed. This was the original conjecture. This was the original conjecture made by Mazur. Afterwards, there was some simplified version. I'll talk about some. And my main result today is this is a forthcoming paper with Vasilin Dimitrov and Philip Habegger, is that we can prove this inequality for large curves. Large in the sense that for any fixed g, there exists a number depending only on g, such that as long as the height of the curve is larger than delta, then this inequality holds. Yeah, height of the Jacobian or the curve. Some people also define it as the curve, as the height of the curve. This some immediate application of this theorem. First of all, particular cases. If we take P naught to be a rational point and gamma to be JK, which is a finitely generated subgroup, then our bound here will say that the number of rational points is uniformly bounded in terms of G, D, and the rank. Here, the dependence on D is really artificial. It is there because we have this restriction of large curves. And D is here only because if we fix D, then there are only finitely many curves with small heights. So the dependence on D is only here. And this is actually another version of Mazur's conjecture, this one. Secondly, if we take P naught to be, say, any q-bar point, but gamma to be the subgroup of torsion points. Right here, we only take finite rank subgroup, and this is a rank 0 subgroup. Then we have a bound that I'll just use CQ bar tau to denote it, but this really depends also on the P naught we chose at the beginning. So this is the size of the torsion packets, if you know that the terminology. It depends uniformly on G and D. Again, this dependence on D is really artificial, and of course, it shouldn't even be there especially for the second one. And currently known results for the first one, in this direction, David and Philippon proved it for the case when J is a subvariety of copies of the semi-elliptic curve. And they also find some examples, David and Nakamaye and Philippon also produced some examples of families satisfying this. And for the second one, there's a recent paper of Holy, Laura DeMarco, and Ye. They proved this for G equals 2 bi-elliptic, but their result is stronger than ours in this case because they have no dependence on D. They really prove this. Otherwise, there are some results in these directions using the Chabot-Coleman method, but all of them, of course, there's some rank condition on the curve. Okay, now let me quickly go through the method of Bombieri, Faltings, and Vojta to see some input we need. And our proof is based on the second proof of model conjecture. Recall that if we have J, the Jacobian of C, on J, we fix a symmetric ample line bundle L. Then this L defines a function from the q-bar points to non-negative real numbers It's called the Nehontate height function. It satisfies two properties. First of all, this function is a quadratic. It defines a quadratic form, or simply in this term, if we take the multiplication by n of the height, it is n squared of the height of the original point. And secondly, it vanishes precisely on the torsion points. Now, if we want to fix our finite rank subgroup gamma in JQ bar, we can always do a map from gamma to gamma tensor R, gamma tensor R. And here in this step, this is almost injective, except that we lose all the information for the torsion. But here, we also lose all the information for the torsion. So actually, in terms of the height function and this gamma mapping to gamma tensor R, actually, we're losing the same kind of information, so we can use it to study this. And it is known that, first of all, this is just RR, and HL hat square root defines a norm on it. Just by the linear extension of this function. All right, now we divide gamma into two sets. For this, for simplicity, I'll just present a case where gamma is finally generated. For example, the rational point case, just for simplicity. Gamma finally generated. Then, in this case, when we embed gamma into gamma tensor R, we obtain a Euclidean space here. And gamma will become a lattice in this Euclidean space, normed Euclidean space. And the division, and Bombieri, Faltings, Vojta, in their method, they divided the points in gamma into two sets, which we call the set of small points and large points, in the following way. They found a C0, I'll explain later this number, and divide it into small points, which are the points with height smaller or equal to C0, and the set of large points. So you may guess is the points with height larger than this number. Okay, now we have, say this is the origin, and C0 is here, the radius. Now, the set of small points is here, the set of large points is outside this ball. Well, for Mordell, it is immediate that the set of small points is a finite set. If I restrict to finite generated group, just because it's a lattice and contained in a closed ball, so it's automatically finite. So for the sake of Mordell conjecture, we don't need to do anything for these small points. But then bounding the number of large points is what we need. And this is what is done in the method. So, theorem. This is Vojta, Faltings, Bombieri, and then it was later on strengthened by David Philippon and Raymond. That the number of large points is uniformly bounded in terms of, I think it's 7. I'll just write it C prime G 1 plus R. C prime G R, sorry. The number of large points is already uniformly bounded. Actually, this number is G times 7 to the power of R, but yeah, let me state it in this way. Every term is. And David Philippon and Raymond, they also proved this result for finite rank subgroup. so that this part here it actually works also for finite rank subgroup. And they prove it using the manifold gap principle. Plus the so-called Voita inequality. So this is a review of the Bombieri-Faltings Voita method. It tells us that now, in order to study Mazur's conjecture, we only need to study the set of small points, which for Mordell is the automatic thing, but now it's the hard thing. Before, okay. And they found this C0. So fact, the property of C0 is that it is linearly in terms of the Faltings height of the Jacobian. This is how they constructed the C0. The whole point is to find a good C0 such that this Voita inequality holds. All right. Okay. Now we see that we want to study this set of small points with height bounded linearly in terms of the HFJ. And we want to bound the number of these points like independent of this HFJ. So what we do is, so it suffices to prove the following thing. Small points are far from each other. Or in mass terms, if we have any two small points in gamma, actually we will prove it for any points in JQ bar, then their distance defined by the Nihonte height called Nihonte distance is uniformly bounded in terms of G and HFJ. And we cannot prove it for the moment, but we can prove it plus some number. Let's say delta not G. And this number is why we are restricted to the large curves. Okay.
I'm sorry, what is the remainder?
It's just a number depending only on G. This is what we can prove, but actually if we can prove this term, then we prove the full Mazur's conjecture in its full.
But you will write it clear, I can read.
What we can do, yeah, what we can do is this.
Everything is positive here? Or not?
Everything is positive. But yeah, everything's positive. This may be negative.
This is the problem. This is the reason why you're limited. Otherwise, you will have a bound. And
yes.
Okay, so.
Just height can be 0. Height of P minus Q can be 0.
It can be 0. So that's why this bound is. Yeah.
You mean different small points or?
Difference of small points. That's the difference.
P is different from Q, I suppose.
It could be the same. If it's the same, then this is 0 here, and it just says that the height of the curve is small, because this is a negative number, I'm sorry. Yeah. If this is 0 here, then we will have 0 greater or equal to a positive number times HFJ plus a negative number. So that means the height HFJ here is small.
I think you really do want to take different points.
Yes. Not different.
Otherwise, you'd be able to just conclude by taking P equals Q that the height must be.
Oh, yeah. Oh, okay. I see your point. Yeah. Sorry. But yeah, what I want to say probably is that P minus Q could be torsion. P minus Q could be torsion. Yeah. Thank you. Yeah. Okay. Yeah. But actually, what we prove is not just for gamma, but really for JQ bar with this term. So that we're done. Let me write down exactly what we do. We prove the following height inequality. We prove the following height inequality for one-parameter families. This is a theorem. Yeah, in my talk, because it's a project, it concerns several papers, so I will make it precise which papers are published, which are preprints and which one is forthcoming. This one is a published one this year. It basically shows that this is true for one-parameter families. So let S be a curve, again, smooth but not projective curve defined over Q bar, and let A to S be an abelian scheme of relative dimension G. And L be a symmetric, relatively ample line bundle on it, so that now we have a fiber-wise defined Néron-Tate height. Let X be an irreducible subvariety, dominant or not, it doesn't matter. Closed irreducible subvariety. Then, okay, this is the setting. I may want to use
You said that you expect this to hold without the extra term delta naught G?
yeah, but under certain conditions.
But then it means that there is no difference, which is a non-zero torsion point, or it seems too strong.
Yeah, maybe I shouldn't say that, because when we put everything in a family, we see exactly what we expect or not. Yeah. When we put everything in family, we see more clearly what is expected. But here I want to explain the idea of what should be proved to get this result.
So you don't claim that you think that...
No, I don't claim that. I just say that if that could be proved, then the conjecture is solved. But no. All right. Now, we assume that this X satisfies some condition, which I'll call non-degenerate. I'll explain what it means later in my talk. Non-degenerate. Then we have two conclusions. First of all is if X is non-degenerate, then we sort of can compare two height functions. The first height function is fiber-wise defined. The second height function is completely on the base. Write it. There exists a number depending only on X, and its RST open, non-empty subset of X such that the following inequality holds if we consider the two height functions. First of all, let me first of all finish this and then explain what I mean. Okay. First of all, my s, small s, is just a point on the base curve. So this function, it means that it actually means HFAS. But I write it in this way to emphasize the fact that this function is completely on the base. It does not really depend on the fiber. And this point P lies in this Zariski open dense subset, but it's also on the fiber over S. So this height function is really the fiber-wise defined Néron-Tate height function I talked above, which is above. So the left-hand side is something depending purely on the fiber. The right-hand side is something depending purely on the base. A priori, there's no relation between them. We can't expect to have a bound. But here, what we proved is that if we assume, if we restrict to a subvariety satisfying some property, then these two heights can be bounded. And of course, in order to make this useful, we need to say that what is non-degenerate. There is an original definition, but it's ad hoc. So here, we also prove that, we also give a criterion of this non-degeneracy. X is degenerate if and only if it's very rigid from geometry. It's simply the translate of an abelian subscheme translated by a torsion section, then by, I would say, something constant. This means that the abelian scheme may have a constant part, isotrivial part, and then the other part of X is just a trivial product up to a finite covering. So in practice, we prove that in practice we can often check this condition to determine whether X is degenerate or not, and then if it's not, then we can apply this. I'll give you an example.
Assume that X is dominant over S.
Yes, it's better to assume it, but otherwise these whole things work because this is just one number. Then, yeah, let me assume this. Yeah, why not?
And but it is not necessarily absolutely irreducible. Only irreducible.
Absolutely irreducible. Everything is defined over Q bar, so it's absolutely irreducible or irreducible.
No, in the total space, but in the general fiber, it is.
Oh no, it's not necessarily. Well.
Yeah, so when you add
this also may not be irreducible. I say abelian subscheme, but of course I mean up to a finite covering with base change, then it's abelian subscheme.
You mean the finite cover of S?
Yeah.
So up to a finite cover of S,
Yes,
it's like.
Yeah. Okay, up to a finite covering of S. Yep.
I'm sorry, what happens if A to S is just a product? It would seem that the two heights are independent.
Then if X is not a constant, then they are not independent.
Sorry?
If X is not constant, then they are not independent. Then this height inequality holds if and only if this X is not a constant thing. So this result a priori also applies to constant abelian scheme. Yes, it does. Okay. The example is this is a preprint with the three authors. We proved this conjecture, the theorem for one-parameter families. Let's have a look. Now, suppose we have a one-parameter family of curves of genus at least 2. For simplicity, I'll assume G is at least 3, just for some reasons we will see. Then we consider its relative Jacobian. Well, there's no canonical way to embed C into J, but because we want, actually here we don't care about the actual heights of those points, but the distance of those points. So the height of the difference of 2 points. So we only need to care about this subvariety C minus C in J, which is well defined because it can be defined as the image of this fiber product to J, where this is fiberwise defined by sending PQ to P minus Q fiberwise. So we don't need to even fix a section for the base of the Abel-Jacobi embedding. Okay, let's call this one our subvariety X, and of course this will be the A over S. Then the assumption of G at least 3. This will imply that X is non-isotrivial family. Isotrivial. Then this assumption will say that X is non-degenerate. Just by computation by hand, X will be non-degenerate by this geometric criterion. Now we can apply this height inequality. Then if we take 2 points on the same fiber of C over S, which are equal to this C depending only on X, so S, so C, and so on, times the Faltings height of the base point. Of course, for PQ satisfying those conditions. But this is an open condition for the rest points. For the rest of points, we use those packaging arguments. But at least now we see that because this number, it depends only on the family, not each individual fiber. So we can see that now we really have this result. So the height of the distance of any 2 points, algebraic points, are uniformly bounded below linearly in terms of the faulting's height. And this is what we want to prove this. Yes, P is different from Q again. Thank you.
So this tells you that if the difference is torsion, then you get still some consequence.
Yes, if it's torsion, then the height of the curve itself is bounded above.
And the P and Q are small? No, not small. They are.
Then the curve is small, say.
But you don't say that if there is a small point, the curve is. You should only say if there is a torsion point. The torsion difference of small points, the curve is small.
Yeah, well, if here P minus Q is a torsion, then the curve is small. Yeah. So that it can be negative, but I mean we can take different normalizations to make it positive. There are different normalizations because our
Yeah, but which normalization? Something it's. Some
convenience of normalization so that this is positive. Actually, yeah. In my thought, faulting's height will always be positive. Yeah. The thing is, actually, we prove this purely in terms of height machine. So it's okay to add a number to this, or 1 to this height function. And this basically proves the theorem for one-parameter families, up to some details for the packaging argument. Okay, now. I hope I convinced you that if we can generalize this height inequality for arbitrary families of abelian varieties, then we can prove the theorem. And then next comes the generalization. And to do that, I will need to explain what is this non-degenerate. You will see that it comes from geometry. To do this, because we want to solve this conjecture, we can just work with the universal curve. And this is the modulus space. This is the universal curve. It does not have a section, but still, it's a universal curve. Here, I'm taking some level structure. And again, I have the universal Jacobian, and I can take this map to construct a CG minus CG inside J, which is well defined. And furthermore, I would like to embed everything in a universal abelian variety, using the Torelli locus, Torelli embedding, to embed it into the modulus space of abelian varieties, principally polarized modulus space of abelian varieties, and here, this one. To curly AG, which is the universal family. So in my talk, I will always work with this system. I have the universal Jacobian, and this is the universal abelian variety. And this is the map pi.
I'm sorry, you fix a level structure?
Yes. Because actually in my talk everything is for height machine, height inequality, and so on. So taking a finite covering, it's always allowed. It doesn't really. Yes. So this is the object we will work on. And then whatever subvariety we take will be a subvariety of the universal abelian variety, but it may not be dominant. Most of the time it's not dominant to the base. Irreducible subvariety. Again, geometrically irreducible subvariety defined over Q bar. Okay. And furthermore, we actually have another object in this picture that is the tautological line bundle. it exists just because the modular space parameterizes not only abelian varieties, but each abelian variety is equipped with a polarization, a principal polarization. So this is a tautological line bundle on the universal abelian variety. And we can take the first Chen class of this line bundle. This non-degenerate condition, well, this is not the definition we take, but it's really the geometric meaning behind the definition we will take in a few minutes. X is non-degenerate if X is called non-degenerate. If we take this first Chen class, we restrict it to X, and we take its correct wedge power, it is not always 0. It is not always 0. Well, one thing about this form is that this first Chen class is always non-negative. This can be computed in explicit or coordinates, and this is done by, I would say, Mach, Nyman Mach. So this is always non-negative. So saying that this is not always 0 means that it's positive somewhere. At one point, it's enough, yeah, because it's a 1-1 form. We have not come to the boundary, so it's really a form. Of course, it's hard. The geometric meaning of this will be then, well, if X is non-degenerate, then sort of if we want to integrate this thing over X, we will get a positive number. So that is almost equivalent to say that this LG restricted to X is a big line bundle, except that now nothing is projective. So it's really the geometric meaning, the geometric background behind. But yeah, but of course, in order to get something, we need to be more precise. But this is our idea. Our description is as follows. We use the so-called Betty map introduced by Daniel Bertrand, Umberto Zanier, Gauchois, André when they studied other kind of Diophantine problems and unlikely intersection problems. The Betty map is defined as follows. Here we take the universal abelian variety. I want to take its universal covering. Well, we know that we take the Ziegel-Arpov space. It uniformizes in the complex category the moduli space. And here on this AG, we want a similar thing. We want a similar thing. And it can be defined as follows. Universal covering of AG. I'll call this one, I was in very bad notation. I'll temporarily call it YG. Yeah. Y2G. First of all, it's defined as follows. First, as set, or as real algebraic object, it is R to the 2G times the Ziegel-Arpov space. And then we want to give it a complex structure. And the complex structure should encode the complex structure of every abelian variety over this moduli space. So it is actually given in the following way. Here we take any vector AB both in RG and a matrix, G by G matrix. We send it to A plus ZB Z. And this is, of course, a bijection, and it's also isomorphism as real varieties, real algebraic varieties. But the complex structure should be this one. Then this is the universal covering. I'll use this one. Now we have Y2G covers AG, which maps to HG plus. This is just the trivial product with some twisted complex structure. All right. Now, X is in AG. I'll take an irreducible component. Irreducible in the sense of analytic geometry, component of U inverse X, then this is going to be in this uniformizing space. This is going to be in this uniformizing space. And the Betti map is something very, very simple. It's just Y2G. When we write it in this way, actually, it projects the first factor, and the Betti map essentially is the composition. This is the Betti map. Well, this is something very, very simple, but it encodes, for example, we can really read off this condition completely using this very simple map. So I'll give the actual definition we have. X is non-degenerate if and only if, or if and only if, this is definition lemma maybe. B, restricted to X tilde, has full rank. The generic rank of this map is twice the dimension of X. So this is because this 1-1 form, it defines a pointwise symplectic pairing. And the kernel of the symplectic pairing are precisely the fibers of this map. This can be computed explicitly. And then saying that this is non-zero precisely means that there should be no direction along X not vanishing along some positive direction of the fiber. So this is precisely the definition. And also from this new definition, we do know what kind of subright is degenerate. Maybe I'll use this one. It's easier. So from this new definition, we have that X is degenerate if and only if for any X tilde in this big X tilde component, it lies in a fiber. So the dimension of B inverse Bx intersect X tilde is positive. The dimension of that is positive.
By the way, the fiber is, the map is just real analytic.
It's just real analytic. It's not complex. The fibers are complex analytic.
And this is used in the verification.
Yes, because it's purist. It varies holomorphically. Thank you. And then this says that now we have actually a curve in Hg plus, a complex analytic curve, such that if we take Bx times this curve, this is inside R2G times Hg plus, it is contained in X tilde. It's containing that for each X tilde. And then it simply means that X tilde is covered by such things. I will use such things.
So the C tilde is just a local curve.
Yeah, but it's complex analytic. You can use analytic extension somehow.
Yeah, but it is just defined a small neighborhood.
Yes. A priori, only a small neighborhood. Yes. And here, I want to say that now then this wholly implies that if X is degenerate, then X is the union of such things, but I can also take the Zariski closure. Right. So X, now when we pass to the universal abelian variety, because X is algebraic, so I can take its Zariski closure. So that now X, if X is degenerate, then it is this ad hoc union. It is this ad hoc union. Actually, the other direction also holds by some lot simpler reasons, but maybe if I have time, I'll explain it. But the other direction is the simple. It also holds. All right. Now we want to study these things. Now, okay. Now the question is to study these Zariski closures. What properties should they have? And this is the next part of my talk, maybe number 3, functional transcendence. I'll start with the weak X-Shanyu statement. This is actually a sort of statement. It says the following thing. If we have two varieties, two algebraic varieties, and this is more or less, this is surjection. This is usually the uniformizing map linked by an analytic map. So both omega and S are supposed to have some algebraic structure, but Q itself is very far from being algebraic. It's highly transcendental, but it's only analytic. Then weak X-Shanyu says that things here and things here, they should intersect transversally, except if they actually intersect in a smaller base, meaning that if we have Z inside omega irreducible, complex analytic, again irreducible in the sense of complex geometry, then the dimension of Z bar inside omega plus the dimension of QZ bar inside S is greater or equal to the dimension of Z plus the dimension of use QZ bizarre. Let me explain this term. So we have a bialgebraic system here, and we say something is bialgebraic if it is algebraic here and here. That is the bizarre thing. So this is sort of the bialgebraic closure. Weak X-Shanyu says that this thing, it is in omega, an algebraic thing in omega, and this QZ is an algebraic thing in S, and the dimension of their sum is at least the dimension of the Z itself plus the QZ bar, the bizarre thing. And it means that these two things, if there is a proper bialgebraic thing containing both, then they don't intersect transversally. Otherwise, they always intersect transversally. So this says that if we have some sort of unlike intersection, then there must be a reason. Yeah. And this reason, we can write it down. This is the result we're going to use. This kind of result was first proved by Alex, of course, to study the schedule functional analog of Shanyu's conjecture. But they got interest again by the study of the Andreault conjecture, and it's a weaker form. X Linderman was proven by Klinger-Ullmo and the FIF. This is for Shimura variety. This is for Andreault. But this general form, recently it's proven by Mach, Pilat, and Zimmermann for the modular space. And this paper is published. It has two extensions, two directions of extensions. First direction is by Baker and Zimmermann for variation of pure Hart structures. This is also published, and this is used in the recent proof of Lawrence-Van Kantesche proof of model conjecture. Actually, it's used for the high-dimensional case. Another extension is done by me for this universal abelian variety. It's a mixed Shimura variety. It's not pure anymore, but this is a preprint. And in studying this question, studying this y, it is this form I'll use. All right. Now to study that y over there, we see what condition it satisfies. We apply the weak X nu to here z will be r times c theta. It is also complex analytic, as we said here. And of course, to this system, to the system y2g to ag u. All right. Well, then first of all, the first term is dimension z bar, which is the dimension of r times c theta zar. This is the first term. The second term is precisely y. And the third term is 1. Well, because it's a curve. The third term is 1. And the last term is, I'll call it y bizarre. Now, in this inequality, actually, we know many things. This is what we want to know, so we don't need to do any operation on it. This is a number. And this is a bioalgebraic thing. Well, in bioalgebraic geometry, usually these kind of things have very good geometric interpretation, so we don't need to do much about it. So the only thing we need to study is the first term. Well, a first step to do is that this RC closure, although this is not trivial, but it's not very hard, actually, certain things commute. We can first of all do the RC closure of C theta completely in Hg, and then do this product. They are actually the same. We can show that. Then the inequality becomes something purely in the base plus dimension of y is greater or equal to 1 plus dimension y c bar. Okay, now let's study this. Well, by the choice of c, we know that y is r times c theta and take the RC closure. So of course, this thing is smaller or equal to dimension of pi y bizarre. This is smaller or equal to pi y bizarre. So now we have the inequality being dimension of y is greater than, I remove this 1, but then replace this by strictly larger than dimension y bizarre minus dimension pi y bizarre. Okay, this is actually the eventual form we want because both things have very good geometric interpretation. I can also tell you what is this difference. This difference has an even better geometric interpretation. Say here we have our universal abelian variety over the modular space, and this is our pi y bizarre. the y bizarre is something over that, and it is part of it. This part, it is precisely up to a finite covering, an abelian subscheme translated by a torsion section, then by a constant section, or isoconstant section. So in some sense, it is the smallest abelian subscheme containing this y. It is something like that. So now y is something here. Say this is y, and if we restrict the orange part to the yellow part, then y will be contained in no smaller abelian subscheme in this whole thing. Then dimension y being larger than this difference means that the dimension of y is larger than the relative dimension of this abelian scheme. And if we look at the dimension, if we look at the definition of the Betti map, of course, the rank of the Betti map cannot exceed twice the dimension of the original variety. So that's why, as long as y satisfies this, then of course y is degenerate. And if x is the union of such things, then x must be degenerate. This is why I said that the other direction is rather easy to prove.
So you say it's an abelian subscheme over what? Over a subvariety of AG?
Over its base.
And it is plus a section?
A torsion section over its base and the constant section over its base. Yeah, now I'm restricted everything in the base.
Yes.
The base is fixed.
Yes.
Yeah.
So what is torsion plus?
It's translated by a torsion section of this restriction and then by a constant section of this restriction. Of course, when I talk about this, I always mean up to a finite covering.
So so a torsion section will become constant after the finite cover? No.
Yes, it is. It is. I just want to separate torsion and constant, but otherwise I can say just constant. It's fine. It's fine. Yeah. But because in studying this mixed Shimura or whatever, this stuff, torsion and constant, they are really very different things. So I like to separate them. One of them is special, the other one is weakly special, and so on. So okay, now using the mixed X channel, we can show that X is really the union of something, and still an ad hoc union, but each member of this union have a better interpretation. It satisfies some condition which is more or less standard in unelectric intersection theory. And then next step is really do unelectric intersection. Maybe right here. So next step, do unlikely intersection theory. Again, this is basically says that the maximal y satisfying this condition, they come from finitely many of families. This actually goes back to even Bogomolov for abelian varieties, and then Emmanuel generalized it to Shimura varieties for weakly special subvarieties. On the other hand, when studying those unlikely intersection, the Zuber-Pin conjecture, Dao and Ren, Habegger and Pila introduced this weakly optimal thing, and Dao and Ren proved it for Shimura varieties. I prove it for mixed Shimura varieties. So we can show that those maximal y's come from finitely many families. So eventually this ad hoc union becomes a finite union, so that it's Zariski, so that for any x this union will be Zariski closed, and also we can prove a criterion when this Zariski closed subvariety is the whole thing. Just doing this unlikely intersection stuff. I don't think I have time for it, but just back to our counting problem. Back to Mazur's question. Of course, as I said, we want CG minus CG to be non-degenerate. Unfortunately, it's not true, just for stupid reasons, because the dimension of this is too large compared to G. So this is not the correct correct X we take. The correct X we take, there are two ways. I'll take the easy, but I'll take the easy way. It's just a fiber product. With p's, I think here I can write 3, but I really should write 3g minus 2. Okay, for some reasons, for some induction reasons, and of course here I'm assuming that g is at least 3. If we take this power to be 3g minus 2, then x is non-degenerate, so that we can prove this height inequality. It says that, okay, we cannot prove that all each pairs of different algebraic points are far from each other, but we can show that around each algebraic point, there are at most 3g minus 2 points which are not far from it. And for the purpose of counting, that suffices. So for each algebraic point, at most 3g minus 2 points close to it. Close means that the distance is smaller than the linear function on the Faltings height. Yeah. Then for the purpose of counting, we're done. Just multiply everything by this number, which still is explicit on G. Okay. I think I'll stop here. Thank you.
Well, thank you. Are there any questions?
Yeah. Could you repeat why you have to rule out the case g equals 2?
Oh, actually, it's just because when g equals 2, this will be the whole thing. So whatever power you take, fiber power you take, it will still be degenerate. The way we...
To that point you don't.
Yeah. But the way we solve this problem, actually, this is not the actual thing we take. We take I know this. So the map we take is, this is k, so this is k. We take is p1 minus p0, pk minus p0. The map we take is actually this one. For this, as long as k is at least 2 or 3, then g equals 2 will also be solved at the same time. Yeah. For one-parameter families, it's almost equivalent to take this one and this one. Doesn't matter. But actually, when we work on this, even for g at least 3, it's simpler to take this one just for the proof. Yeah.
So I think with Joe Harris and Lucia Caporazzo, Barry has been even more optimistic about rational points.
Optimistic. I don't know.
Yeah, for that thing, I really don't know because it's a rank stuff. I can do nothing with the rank.
No, that's different.
Yeah. But I have a question about it. So you do it for finite rank subgroups of JFQ bar, and of course also J torsion.
Yeah.
What about a sum of finite rank and J torsion?
I think it's a finite rank, right?
What?
It's a finite rank, right?
What?
It's a finite
No,
rank
but I mean,
Q rank.
Oh no, I don't mean that. I mean the visibility of if I allow myself to divide a finite rank subgroup by integers n, I get a.
Oh, that's actually what I mean by finite rank. It's Q.
That's what you mean
yeah,
by
yeah,
finite
yeah. It's
rank.
Q
Okay,
rank.
perfect.
Yeah. By finitely generated, I mean that it's a Z module a priori, but finite rank is really over Q. Yeah. So the divisibility, because in the proof, actually, for the large points, they already solved this problem, and for the height inequality, we actually don't see this gamma. Yeah.
Any other questions? Okay, well, thank you, and remember, we start again in 10 minutes.
Thank you.